Okay, thanks, Kim. Whenever you want.
Okay. All right. So the plan for now is I'm going to step through the whichever GRB I said it was, GRB 250504A, to show how to do some of the things, run the pipeline and extract things in Xselect. So what we went through in slides this morning, but sometimes it's just easier to see what's going on if I type stuff. So if any of you want to follow along at the same time, that might well be a good idea. Obviously, you don't have to if you don't want to. And then after the coffee break, a suggestion is that you can either have a go at this one or at something else, or ask us specific questions that you might want to have a go at. So you are welcome to ask questions while this is happening now, but also there will be the hour and a half or so after the coffee break. So, and it's not just me here to answer questions. Everybody involved with the XRT should be able to help, certainly for the XRT session. Okay, so as said, we're going to look at GRB 250504A simply because it has XRT and WT stuff, and I'm just going to hold on a sec. Just getting my notes so I don't actually forget to cover something. That was the plan. Right, okie dokie. So if anybody is wanting to follow along, hopefully you have the data that we suggested downloading. So it's this OBS ID here, and within it, to run XRT stuff, you need the auxiliary directory and the XRT directory, which has event and HK subdirectories. So I'm going to do this the way that I would generally do the observing. So when I run it, I make a directory on the same level. So you can see we've got the input directory that I just showed you, whoops, that one, and I've just made an empty output directory. How much? I mean, if it gets much bigger, then I'm looking on the screen, not up there, because I can't. I mean, how big do we want it to be? Is that? I mean, I can probably. Or I'm not sure how big it will go before it goes up. Okay, so hopefully that's okay. I mean, I can try a bit bigger. Hold on, let's see how big it gets.
That's okay.
Yeah. Okay, it does of course mean everything's gonna, even if I widen the window a bit, things will probably wrap over a little bit, but we'll have a look. So we have the input directory, this one. I've made an empty output directory and I'm going to go into that, and that's where I'm going to run XRT pipeline. So as I suggested earlier, XRT pipeline, it occurs to me that I didn't, the correct LC equals no is it speeds it up a bit, because that means it doesn't correct the light curve that it extracts by default, but seeing as that light curve is useless, we don't need it correcting. So correct LC equals no speeds things up a bit, because the corrections can be quite slow. And as I mentioned, can be useful, cleanup equals no. I'm going to include that, so that will keep extra temporary, what would usually be a temporary file if I didn't include cleanup equals no. So it will keep those so you can see what they look like. And I am going to write everything out to a log file, so that it's all the information is there. But everything else I'm going to let it prompt me for. Now, that is not the RA for the GRB. So, and as you may have noticed, previous inputs are kept in the, it will show in the square bracket the last input that you used for that prompt. And this is from a NOVA that I was analysing yesterday, I think. So I'm just going to pop into this window, because here is one way to get the best position for the GRB. So the swift.ac.uk XRT_positions is our website, which keeps all the lists of the positions for XRT detections of GRBs. And 0504A is there. So I am just going to copy these numbers into my prompts. At least I am, if I can control my trackpad. Okay, so I've given it the RA index. As we mentioned earlier, if you're analysing something for which you don't know the coordinates, you can just say object and it'll be roughly there, hopefully. But for window timing mode, it's really helpful to have the RA index. So the target input directory is this, the one that I showed that has that we downloaded. So in my case, it's ... that. So because they're at the same level, you can ignore the long path for the in my square brackets because that's within our Leicester systems, and the rest of you wouldn't be able to do that. And then the target, the stem for the fits is always the SW followed by that same opt ID that we're processing. And I want to output it into the directory that I'm here. You can, so when it says directory for outputs, if you can write everything to an entirely new directory if you want. You don't have to have created a directory and run it there. I don't know why I do it that way. I just always have. So it'll take just a little while. I purposefully didn't pick one that would take ages to process. I mean, none of them should take all that long, but there we go, it's done. So if I ls, then we can see all the many files that have been produced. So we have things, so MKF, and we have MKF and HK. These are, well, the HK is the housekeeping file, MKF is the make filter file. It's information about the housekeeping, the observation, behind the scenes, stuff you don't usually need. This here is the exposure map for the whole of the PC mode. And there's a window timing mode one as well. In fact, let me just do, there we go. So these are the exposure maps that we have. It even creates one for the window timing settling data, which is no use to us. So you can ignore that, but we have a PC and a WT one. The cleaned event lists, which is what we're going to work with. Again, it creates them for the slew and settling data for the window timing mode, but we can't do anything with that. We do, however, have two pointing ones, the PC pointing and the WT pointing. And the other vaguely useful files are, because I included cleanup equals no, the region files were kept. So these will be circles centered on those coordinates that I used as the input file. So once we've got to this stage, we can open up Xselect and start doing stuff. So as I said, the session name, I just always leave as a default because I never do anything with it. Note, by the way, that until you read in data and it knows that it's Swift, it currently defaults to thinking it's Chrism. Used to be Asker, then it went to Suzaku, and now it's Chrism. So I will try and remember to write out the whole word, as I mentioned, even though I wouldn't usually do that. So I'm going to read in the window timing event list to start with. So it will prompt me for most of the bits. So I've said read event, it's in this directory where we're running, and I'm giving the window timing cleaned event list. And that's when it says, got new mission, Swift, reset the mission. Yes, absolutely, we want to do that. And so here we have this bit of basic information. So first of all, we want an image, and I always do this filter PHA cut 30 to 1000 so that we have it over 0.3 to 10 kV, which is really the only energy range that's the biggest energy range that's useful for XRT. You can, of course, do smaller energy ranges if you're interested in hardness ratios. You might want to compare 0.3 to 2 kV with 2 to 10 kV. Then you would do a PHA cut of 30 to 200, and then later you do 200 to 1000. So I have filter PH8. So now if I extract image, it will extract me a window timing image for the entire exposure over 0.3 to 10 kV. It tells me we have 53 seconds of data, and in the whole of the field of view over those 53 seconds, we have a total of 324 counts. So that count rate is not precise by any means, because it's not just the source itself. I mean, most of it will be the source because it's window timing mode, and that should be significantly brighter than the background, but there is some background things. So it gives you a rough idea of the count rate though. So I've extracted the image. I can therefore plot the image, which I will definitely make bigger. Oops. All right, so there we have our window timing strip with a bright source in the center. My DS9 is set to plot log scale automatically because that's usually the most useful for XRT analysis. For anybody who is not used to DS9, if you sort of right click and drag your mouse across, then it changes the scaling, which might make things easier to see. And you can also zoom in if you want to see it a bit bigger. So there we go. So here we have our 200 pixel wide window timing window at the roll angle, as I mentioned this morning. So if I go to region and open, and let's make that wider so we can see, this is why cleanup equals no can be useful when you run the pipeline, because it will automatically have as a circle at the correct, the RA index that you gave, which just saves you extra typing, honestly. So there we have a circle centered on the source. Now, it may not by eye, you might wonder if it really is centered, and that's mainly because it's over the bad columns. So remember I mentioned that we have bad columns because the micrometeoroid hit the CCD and we had to mask bits out, and they appear obviously just as gaps in the data. So it's sometimes it doesn't look like it's quite centered, but I know I used the right coordinates, so it's okay. And so that will be our source region in this case. For a normal, simple window timing thing like this, usually what I would do is just have a similar sized region, still within the window, obviously. So all this space out here it's outside the window. So it's not just that it's not bright, there are no counts there. So there's no point putting a region there, but there are, because the background is low, there are gaps. I mean, you can see there aren't counts all the way across. So that is what I would usually do for a simple window timing thing, just a normal circle, same size as the source. But I thought it might be useful to show how to do the big background annulus that we mentioned in the slides, for which is useful when you have multiple roll angles, just because that's a little, demonstrating that can help a bit, I think. So, so I haven't saved this circle one, so I'm just going to delete it. But what I want is an annulus. So region, shape, annulus. And that's going to be centered on my source. But the thing about this, which may seem counterintuitive, but is going to be fine, I promise, is to create a big annulus that goes over the edge of the window timing window. So, as I said, the window strip is 200 pixels in diameter, therefore 100 pixels in radius. And what we want for a giant annulus like this, to do this special method, is you have the inner annular, the ring, so this bit, and the outer one have to be symmetrically placed about 100 pixels. So I've got 80 to 120. We could also have 70 to 130 It's got to be the same on either side of 100. So this means that we will always have approximately, so that this goes, as I said, from 80 to 120, that's 40. Sorry, I'm going to sneeze. Excuse me. So that is between the inner and outer radius, we have 40 pixels there. At all times, those 40 pixels minus 1, because although we say there are 200 pixels across, actually the end one is masked out, so it's really 198. It doesn't, one or plus or minus 1 pixel makes absolutely no difference. So if you forget this extra bit, it doesn't matter. But this means that no matter what the angle of the strip and wherever the source moves about, we will always have this 40 pixels minus 1, so 39 pixels in the error region. So I'm just going to save that annulus before I forget. So region save. And I'm going to call it background. No, I'm not, because I can't type. Window timing background and dot reg. The names obviously are whatever you want to call them. But do make sure that these things are saved in FK5, so WCS FK5 coordinates, so that it's saved in proper RA and DEC, not in CCD coordinates. All right, so I've set up regions. Now I can actually think about extracting things. So the first thing I am going to do is to extract a light curve, and I want a source light curve to begin with. So because I'm going to use the region that was produced by XRT pipeline, it has, oops. It has a rather long-winded name because it always uses this standard of SW for Swift, the OBS ID, and everything else. So it's if you're going to use it often, you might want to rename it to something that's easier to type. But for now, I'm just going to stick with the default. So I've filtered on this source region, and now I'm going to extract a light curve. So extract curve. So it's done that. It's told me we've got 270 counts. And the count rate is about 5 counts a second. So if I now plot the curve, we have 2 snapshots. Well, really one and a very tiny little bit there. So all the window timing mode useful data is in this first snapshot for this window timing, for this GRB observation. The fact that we basically just have one bin there, this is because we slewed back to the GRB for a second snapshot, and it was in auto mode at this point. So it started off in window timing mode, and then realized that it was absolutely not bright enough. There weren't enough counts in the central, count rate wasn't high enough in the central field of view to warrant staying in window timing mode. So it moved automatically straight into PC mode. So we've basically got one frame, I think, of window timing mode there, which is no use to us at all. So we just want this first snapshot. So I'm going to, when you plot a light curve, it takes you into the PLT command. So iPlot, the interactive way to use pgplot. So I'm going to quit out of that to bring me back to the xselect prompt. But I just want to filter on that first snapshot. So the easiest way when it's for an entire snapshot like that is to say, whoops, sorry, typing and talking at the same time is not my forte. So filter time cursor. So I'm going to do that so I can choose that first snapshot. So when you do filter time cursor or filter time spacecraft clock, it will bring up this stuff here. It gives information. It tells you how to do it. Basically, what you do is you type quit, and then you click where you want to include. So I'm going to type Q for quit because I'm not typing absolutely everything. And so I want to click just somewhere before the red data points start and somewhere after they finish. So, I mean, I could click from there all the way to there. It would give me the same result because there's no data there. But with the cursor still in this window, you press the letter X, and then that will write the timing selections to a file. If you realize you've done something wrong, you press, excuse me, C for cancel to stop whatever you chose, and if you realize you'd clicked somewhere wrong. And the alternative, so I'm just, say you pressed X to save it and then thought, actually, no, I don't want to do that. You can just say clear time cursor, and that will get rid of it again. So if instead of you doing filter time cursor, you do filter time SCC, so spacecraft clock, to do that same interval, I would tell it to filter from, well, you still do Q to bring it to the start. And I would say, well, I want it to start at 0 seconds because there's nothing before then. And then, well, I mean, we actually know it's about 50 seconds. So we know it's very clearly less than, say, 200 seconds, because that's the first tick mark. So if I say 0 to 200, and I'll just bring that window back so you can see it, it's drawn a line across, and that's basically giving me the same results as if I'd done filter time cursor, because I've chosen the same interval. So this time you have to press X in the where it says enter start and stop times rather than in the window, because you're typing rather than using the cursor. If for some reason you want to keep that GTI file, so for example, you want to keep the timing to extract data from, SWOM or EP or GBM or something else that's observed at exactly the same time, then there isn't actually you can't easily just save that timing selection. The best way to do it is to copy that GTI file to something that will not get deleted. So for now, if I do a different time filtering, or if I come out of XSelect, that timing selection file will just disappear. So I want to save it to something else. You can run other commands within XSelect. So commands you would usually run at the standard prompt, you can run by preceding them with a $sign. So if I say $ and then copy that to, I don't know, I'm going to call it window timing 1.gti, because it's the window timing first snapshot and it's a good time interval. So that has now saved that file. So that's there. It won't disappear when we come out of XSelect. So if I now extract a curve for that time, extract curve and plot curve, I am going to start abbreviating some of these typings because it's going to take too long. So there we are. We have that first snapshot in window timing data. The second bit with just one bin has gone. We've got it at 1 second because that's the default time binning. So if we wanted to bin it up a bit more, we could say set bin size 10 if we wanted it in 10 seconds. So it's always in units of seconds. And if I extract the curve for that, you'll see we now only have 5 bins because it was about 50 seconds long, and we've got 10-second bins. Okay. So that is for the source region. So I'm going to save my light curve because, as I mentioned at least once this morning, the XSelect doesn't save anything by default. So I'm going to say save curve WT because it's a window timing light curve. But we also want a background light curve. So if I get rid of the region, clear region, that means I'm no longer just filtering on the source region, but filter region window timing background annulus, this big thing that you can still see that I created. If I then do exactly the same, so it's still got the timing in there. I didn't tell it to stop doing just the first snapshot. I don't need to do that again. All I need to do is change the background region. So if I extract the curve for that, we'll see that we have a grand total of 4 background counts in the approximately 50 seconds of data that we have, because our background is low. So I plotted that just to show you, but now I want to save the window timing background. So I should have said, if you tell it to save a light curve, it will, if you don't give it a dot something, so if you don't give it a suffix, it will call it .lc for light curves. That's the default, and it makes sense. I mean, LC light curve, you can call it something else if you want. It won't actually change the file. It's a fits file, so you could call it .fits if you wanted, but the default is to call it .lc.
Show status so you can show that.
Thank you. So show status, as Andy has just suggested, will remind you of the commands, the filtering that you've already done. So let's just scroll up a little bit.
Probably one of those sheets of commands next.
Yes.
If you get where you are, or you type it, or what you can track it.
So, I mean, it tells you things like plot devices X windows. I mean, some of it is not particularly useful, but it tells us that we're binning at 10 seconds. It reminds you what the minimum time resolution for window timing mode is, so you can't do anything shorter than that. And yes, it says it's reminding us that we've filtered from 0.3 to 10 kV or 30 to 1000 PI channels. And currently I have that window timing background annulus, and we have the timing selection. So yeah, show status can be very useful. What it doesn't tell you is whether you've typed save or not. So I mean, I did, because I did it there, but and I managed to capitalize curve. Didn't realize I'd done that. Yeah, show status can be very useful. So now we have a source and a background light curve, but we probably want a spectrum as well. You don't have to extract a source before a background. You can do the background spectrum before the source spectrum, and seeing as I've got the background region in, I'm going to the background spectrum first. But the important thing for the spectra is you need to get rid of this PHA filtering. You must not extract the spectrum with any PHA filtering, because it won't match up with the calibration files and you won't be able to do anything with it. So the command to get rid of anything in Xselect is always clear whatever you did. So it's filter whatever, but clear whatever gets rid of it. So now if I type extract spectrum, I will have a window timing background spectrum for that first snapshot. So I can save that. I always call my spectra.pi because that was what I was taught when I was doing my PhD. But if you don't type .pi, if I just typed WT back, in fact, I can do that as well, Xselect calls it .pha by default. I mean, you could call it .spec or something if you want, but whatever you do, as long as you know what you're doing, that's fine. But that WT.pi and the WT back.pi and WT back.pha are identical apart from the name. So I'm now going to clear the region and go back to the source region because I want source spectrum as well. Oh. Yeah, this is what happens when one tries to demonstrate. So filter region and the name of the region. It has to be told what it is that you're filtering, not just the name. So if I extract a spectrum for that, I can save my spectrum as WT.pi. And for a pile-up perspective, I said earlier, window timing mode is piled up above 100 or 150 counts a second. I usually say 100 counts a second. I think our user objects actually uses 150, so I'm more cautious, shall we say. But you can see that given that the count rate here is 5.6 counts a second, if you'd extracted a source spectrum or a source light curve and it had a count rate that was approximately 100 or more, you would want to stop and go, no, pile up, need to do something about that. But in this case, we don't. Okay, so this is everything for window timing mode that we're interested in. So I'm going to show you how to do the light curve corrections and spectrum corrections for window timing mode, and then we'll do PC mode. So I can either exit out of XSelect, or I could put it in the background, but I'm just going to exit and we'll come back in later. I'm just going to close my DS9 window because there's a bit too much there. So I've just thought of something else I should have done. I should have show you how to extract an event list so that I can show you how to build an exposure map. So, this is the joys of trying to demonstrate. Sorry, guys. So all I'm doing is going back to what I did previously, and I'm just rereading in my event list. It won't actually make much of a difference in this case because the second snapshot was only 1, maybe 2 seconds long, so it won't really be statistically different, but I want to show you the method to do it. So I need to go back to the extract curve.
You've got the GTI. Time file.
I have. Fine, I will show the filter time file example as well. Do you want to do this, Andy?
No.
I very seldom save GTI files, which is why it had already gone out of my head that I'd done that. But it does mean that I can show you how to do that. Yeah, so I've read in the event list. And just to remind you what the curve looked like, we had that and we had that one bit at the end. But what we want to do is filter time file, and it will prompt you for it if you don't type it on thing, and I called it wt1.gti. So now, just to prove that it's worked, if I extract the curve again and plot the curve, we just had that first snapshot. So filter time cursor, filter time spacecraft clock, filter time file, as long as you have the GTI, give all the same results. But what I actually want to do now is extract an event list for this one single snapshot. So I would say extract event. And again, the important bit to remember is you need copy all equals yes, so that it keeps the bad pixel extension. Otherwise, that information gets lost and you won't be correcting for the bad pixels. So once you've extracted it, you obviously want to save it because you have to save these things. So save event, and I'm just going to call it WT. At that point, it will ask you if you want to use this event list that you've filtered on. If you do, and you just want to do more stuff on that first snapshot, you can say yes. If you don't, then you would say no, but you'd still actually really need to do clear event. Otherwise, things get confused. But as it is, we are coming out of XSelect now because that was going back to where we were before. So light curve, I will show you how to correct the light curve first, and then we'll do the spectrum. So the light curve command is xrt lccore. So I'm going to do it twice to show the different sets of corrections that you can get. So if we wanted to do the default thing, which will give us a correction every 10 seconds, I would just say xrt lccore, and then it will prompt for things. And goodness, this was last time I did this was running one of your scripts, Andy, hence that bit there. So I am saying none here. I don't want to give it a region file. I'm giving it the actual light curve file to correct. So that is here. I called it wt.lc. So this light curve is the one we want to correct. And then we have to give it a name for the correction. You could stick with the default, but I have a very set way of how I name my things. So I always say wt_core.lc. So I know that that's my corrected light curve. And then the name of the output file is the file that will have the corrections in it in case you want to know it. And my method is to call it wt.core. Andy's script called it long, complicated thing, core fact.fits. You can call it what you want. Again, it will be a fits file. Then you need to give it the attitude file. So let me type that and then say what I'm doing, because otherwise I will get it wrong. Oh, what? Do I what? It's the auxil directory. Yes, thank you. So much easier to do this without an audience. So the attitude file is in the directory that you downloaded. So within the directory downloaded, you'd have an auxil file, auxil directory, and the, excuse me, XRT directory. What we want is a thing called pat.fits. Usually, every now and again, the pat.fits file will not be there. There will, in that case, be an sat.fits file. The SAT means spacecraft attitude file. Can't remember what the P stands for. They are very similar, but the PAT file occasionally has an extra correction. It won't make any significant difference. It's just if the PAT file is there, use that one. So this is, it creates things called instrument maps as well. So we'll see that afterwards, but calling it default is absolutely fine. And then you need to give it the cleaned event list, the one that we've just been reading into xselect and doing stuff with. So that's the _cl.evt file. And then the other thing that we want is the housekeeping file. And that is in the housekeeping subdirectory of the XRT subdirectory of the thing that you downloaded. If you go away. So XRT HK and then the long name that ends hd.hk.gz, or if you've unzipped them for some reason, not GZ, that bit is unimportant. So there we are. That just ran very quickly and it has created me this corrections file. And so if I just bring that up, and I have no idea if I can make that any bigger. I mean, I can expand, but I don't think, no, FV doesn't do that. So apologies, that may not be very clearly visible to some of you, but it's basically what we have is a correction factor for every 10 seconds. It tells you the start time for each of those. Start time?
It's a start time.
Yeah, it's the start time of the 10-second bin. So that's there. You may or may not need to use that for something in the future, but I'm just going to close it. And I just want to show you the other way to do this. So that will be with window timing, WT. Why do I keep almost sneezing? WTN frame equals 0. So this will give us one correction per snapshot. Now, even though there was only one bin in the second snapshot, we'll still get something for it, as you'll see in a minute. So the only thing that I need, so it won't overwrite things. So I'm going to call it _core2. Usually I'd only do this once. This is just to demonstrate the difference for you all. Again, .core, WT2.core. But all the input commands are exactly the ones that we had before. So the attitude file, the cleaned event list, and oh, bother. But of course, it gives the same to the raw instrument map. So I am going to have to overwrite it. I'd forgotten it created those. So clobber equals yes will overwrite these raw instrument files that we don't care about anyway. So if I look at this new WT2.core, so this is the correction factor we've got for this one, and instead of having the 5 or 6 lines that we had previously, now we've just got 2, and this is the correction factor for the first snapshot, and this is the correction factor for the second snapshot that only has a bin or so of window timing data. So we have the output light curve, and this is a source light curve, so we want to subtract the background. And to do this, we would use ACME. Now, if you use the same size extraction region for window timing and just move it along the window, then you wouldn't need to bother about the scaling for the background. That will come up in a minute. But we used, in this example, a bigger region, well, a different size region, actually. So 20. No, it is the same size for this one, isn't it? Because it is the same size for this one. But I will show you what you would change. Oh, goodness me. All right, so XRT, to correct it, we run ACME. So, see, I've already done this one recently, but I'll type it in again. So WT core.lc is my corrected light curve. And WT back is my background light curve. And WT underscore core underscore sub is what I tend to call my background subtracted light curve. So I know that it's being subtracted. The scaling factor for input is just going to be 1 because that's why we're using WT underscore core. It's being corrected. And if the background were a different size, then we would change it here, but it isn't because I used a 20 radius for the circle and for the annulus. So it'll be different when if we do PC mode. You may well see this. Don't worry, it's just because our background is low, so you don't necessarily have a background count in the first or last light curve bin in the time that would match up with the source thing. Generally, if it says warning, you don't need to worry too much. If it says error, clearly you do. But warnings, a lot of the time, not always, but a lot of the time can be ignored. So I'm just going to plot that light curve quickly so that you can see. So there's an F tool called fplot. So if I say fplot and the name of my corrected light curve, x-axis is going to be time because it's a light curve. And then rate, and in square brackets error, means it will plot the count rate with the error bars. So the error in square brackets means it will do the error bars. Those, it's just going to do all of them. It's going to, so we plot it in X windows. Any legal plot commands, you could put things in there to tell it to change how you're plotting. For now, I'm just going to skip it. Oh, no, I should have done space, not that, never mind. But there we have a light curve. So if I'm just going to keep that one there, but put it in the background for a sec, because what I also want to do is to compare to that. Right, so let's do it. Yeah, let's do it that one on the left. So the one on the left is the light curve that we extracted from XSelect with no corrections applied and no background subtraction. The one on the right is corrected and with background subtraction. So this one on the left, that top tick mark is 6.5. So this bin, actually, yeah, well, the center of that bin is slightly below 6.5, but it's round about there. Whereas this one, you can see is higher. The center is around about 7.5 counts a second. And that's because we've applied this PSF correction. So they've all been shifted up by that, whatever the factor was in that correction factor that I can't remember. So I am going to come out of my two light curves. So that's how you extract and correct a light curve. Now we want to do stuff with the spectrum, that's what it's called. So we want to build an ARF file, and for that we need an exposure map that is over the same time, and that's why I extracted the XRT, extracted the event list. So just give me a minute to type this and then talk, because I will get it wrong otherwise. So unfortunately, I can't, it won't let I put attitude minus instead of equals. Sorry, let's change that. I'm using tab to autocomplete commands, and in the way I'm running this here, I can't straight after an equals sign, which is why I put in a space, and I now needed to oh bother to ignore that. So this is why I'm going to type it, and then I'm going to explain things. Andy, if you see me typing something wrong, tell me, because it's really difficult to do this with an audience. Did I call it window timing or window timing 1? Oh, okay, apparently I just can't type today. Right, let me just check that's going to work. No, oh no, XRT Expo map. Sorry. See, this is what happens when I try and type while I'm teaching. There we go. Just wanted to make sure I had typed it in right. So there we go. Back at the bottom, this is what I typed in. So you have to give it the attitude file, which is that PAT file again. You have to give it the HD housekeeping file, which is the one in the XRT directory. And then you tell it the name of your event file. Stem out is what the output file for the exposure map is going to be called. It's a good idea to make sure it's the same as your input file, because that way you know what matches up. And you have to tell it what output directory to write it to. So out dear, and I'm telling it to write it where we are. And so we have all this stuff written to the screen. And the important thing at the end is that we have an exposure map. So if I just show you what that looks like. There we have a window timing exposure map. So we've got the bad columns that are marked, bigger set of bad columns and a smaller set of bad columns. And it's at the roll angle. That's why it's tilted. So now we have that, we can actually do stuff with we can build the ARF, which is what we want for the spectrum. So to do that, XRT make ARF. So XRT make ARF is the relevant tool. And you say expo file equals, not expo map this time, the name of the exposure map that you've just created. And it will prompt you for everything else. Again, everything can go on a command line, but this is an easier way to demonstrate. So you give it the name of the input spectrum file. Apply PSF correction, yes, that's why you've got the exposure map and everything. We want to correct it. And then the output, you can just call it wt.arf or whatever you want, something like that. And then if we use -1 for the coordinates, it will work it out from the center of the information in the spectrum that tells it where the center of the extraction region was. And so that is all good. This here, this percentage of fluence within the ROI, that's the correction factor that is being applied. So, well, not the correction factor. The correction factor is 100 over that. So the correction factor is 1.367 if we need that for something, and I'll show you what you might want to use it for very shortly. All right, so we have a window timing source spectrum and a window timing background spectrum, but this is where we have to take into account the fact that we use this annulus. So if you use a circle and just move it along, the area is the same, and it doesn't matter that it's just along the strip and the rest of it's null and void stuff. But for the annulus, obviously has a much bigger radius, much bigger area than the circle, and XSpec can't cope with that. So you have to tell it basically, you have to tell it the equivalent of what the radius, or in this case diameter, because it's just one dimensional, what the settings are. So Oh, it's 1, not 0. See, everything that I will mistype here, I would usually type perfectly the first time. Sorry. So there are 2 ways to do this. FPARKey allows you to edit a header keyword directly. So I'm telling it to set the backscale, so that's the backscaling keyword, to a value of 39, because we had the radius went from well, it went from 80 to 120 pixels. So that's would be 40, but we lose 1 because there's one of the end pixels will be masked out. So it doesn't matter if you forget and put FPARKey of 40 instead, because 1 pixel here or there makes no difference, honestly, and there are other reasons as well. The alternative is you could actually use FV to open the file, find where the backscale thing is, and edit it to say 39 instead. But FPARKey can be quite handy. But you also need to do this for the background file as well. And it occurs to me that the source should actually have been 40 and the background should have been 39, but never mind. Yes, it doesn't matter. So honestly, 39 or 40, 1 plus or minus a pixel is not a problem. So this now means that when we fit the spectrum in XSpec, it will know that the background isn't from an area that's much bigger or much smaller than the source, because otherwise it ratios the count rate. So if it thinks it's from a much bigger region and the count rate is over a much bigger region, it would confuse things no end.
So XSpec takes the backscale keywords from both files, the source file and the background file, and takes that ratio to adjust what it thinks the background count rate should be when it subtracts it off the source spectrum.
So to get the last bit to get the spectrum in the format that we want is to use, or format for XSpec is grp-pha. So what we do is give it the name of the spectrum, and as I said, if we want to overwrite the same one, you just precede the name with an exclamation mark. You can call it something else if you want, and then you don't need the exclamation mark, but I get so many files, I'd rather just keep them to a minimum. So that was when I typed group incorrectly last time. So what we want to do is to set everything below 0.3 keV to be bad, and then so we can do this one command at a time. Let's do it that way. So I've done that, and then because we want it, we need this 1 count per bin to fit within cache statistics in XSpec. I will say group min1. We also want to tell it what the background file and the ancillary, the R file are called, because WT. So XSpec will read them in automatically, so you don't have to type them each time. And we also need to tell it what the response file is. Now, this is the one that's in the calibration database and that you don't build yourself. I actually know the path length to ours, so this will depend where, if you have the CalDB installed on your machine, it will be in there. And when you run XRT Maker, it tells you the name of the CalDB file. So if you have it installed, it'll be on that path. If you're running the remote access CalDB, then it will tell you what has to be used. I'm not used to that one. If you want, you could copy it into your local directory, but you certainly don't need to. It can cope with a long path length. It may whinge at times, but it's fine. So I am exiting out of that. If you realize that actually you don't want to save anything, if you type quit, it won't save it. Exit does. So in many places, exit and quit do the same thing. In group PHA, they don't. So we have a spectrum that we could fit. yeah, we'll do a very quick fit of the spectrum, and then we'll go back to PC mode so I can show you how to deal with pilot for PC mode. But we'll fit this first. So ignore that. That's an old local model that Andy built, and it doesn't get read in anymore. I should really figure out how to get rid of that. Yes, I am. So ignore, please. Anyway, so I don't know. I suspect some of you have used XSpec before, some of you may not have done, so I'm just going to do a very quick basic spectral fit just to show you how to do it, and nothing more complicated. If you have questions later, you're very welcome to ask. So to read a spectrum in, the command is simply data and the name of the spectrum. Don't worry about this bit. Again, it's a warning. You can ignore warnings. Andy did try to get around this. Or no, actually it wasn't this, but anyway, it's a warning. It all works fine. So it shows you all the information. So when we did XRT Makeoff, and we did, let me bring that back up. We had this correction factor, remember? So the 100 over the number in the ROI as the correction factor. Well, this count rate here that is listed by XSpec, that is not corrected for the lost counts. So if you actually want to know what count rate this spectrum is, it would be the value that's given there, the net count rate, so 5.522, multiplied by this correction factor that we got from the R. So 5.522 multiplied by that. So in this case, our mean count rate for the spectrum is 7.55 counts a second. If you remember from the light curve, it was up at 7.5-ish. So happily, the light curve and the spectrum agree. They really should. All right, so I have a spectrum read in.
Would you say that it's very important that you see the name of an R file?
Yes. Yes, if you haven't read it in, or you mistyped it, or you forgot the R, your fluxes will be utterly wrong. I'll show you, in fact. I'll fit it, then I'll remove the R and show you what the difference is. So yeah, always make sure. If you haven't read in an RMF file, it won't let you plot it in terms of energy. So you will realize straight away. But for the R, yeah, you can actually fit without an R and not realize. So right, so I brought up the X windows. If I just type plot, this is not going to be much use. It's in terms of channel energies, and it just looks a mess. So what we want is set plot energy. So this will be in terms of kV. There are other units you can do, but we're not going to that now. So if I type that, that also looks weird, right? And that's because it's in log space. And right now it thinks we've got things going down to 0. But if I say ignore bad and type that, because we set everything below 0.3 kV to being bad, it's ignored that bit. But really, to be on the safe side, if we say ignore below 0.3, so you can either say ignore 0-0.3 or star means as low as it goes, or as high as it goes. So if I do that, that means it ignores everything that's outside the calibrated range for XRT. It's still going to look a bit weird, and that's because we're used to plotting these things in log space. So if I say plot log data, it looks a bit better, but also a little bit messy. And there may be some of you who are used to doing things like this, and maybe have been told or have used fitting in terms of chi-squared when you need about at least 20 counts per bin. Then the spectrum looks nice straight away. This is 1 count per bin, so doesn't necessarily look nice. But if you say something like set plot rebin, you get a nice looking spectrum. So this set plot rebin command does not change anything scientifically. It just shows, so it doesn't change the spectra for fitting. It just shows what it makes it look neater on the screen. So the 20 and 5 on numbers that I know happen to work well. It's it's something to do with the signal to noise and how many bins you're allowed to combine. It's in the XSpec help, but from past experience, if you have a bright spectrum, set plot rebin 25, it's probably nice. If you have one that's a bit fainter, you might want 10-3. So I think it's probably a maximum of 20 bins to the signal to noise of 5. But again, it's in the XSpec manual. So we probably want to I'm just going to do a quick fit of that with an absorbed power law, because it's a GRB and things tend to be absorbed power laws. You might just want to fit the absorption free, and in fact we're just going to do that for now because I want to try and get through a bit more before we have the coffee break time. But again, later you're more than welcome to ask questions. So no, you're right, that's because I was going to type something else. So we're going to model it as a power law times absorption. It will prompt you for all the numbers, and honestly, usually the defaults will be okay. We'll see if it fits okay. But the one thing to remember about XSpec, if you're doing it as I'm saying, and we do group min1 and use cache statistics, XSpec defaults to using chi-squared. It expects you to be using chi-squared. You can set this so that it won't, but assuming that you haven't, you have to tell it that you want to use C-stat. So C-stat means cache statistics, near enough. So if I now type fit, it did work. Look at that. And we have a perfectly acceptable power law spectrum. Again, for anybody who might not know much about XSpec, these errors, they're 1 sigma, but don't trust them, because I mean they're obviously being shown as symmetrical, and the errors often won't be symmetrical. So it's much better to run the error command if you want to. So if we want to know what the photon index, the error on the photon index is, and for X-ray astronomers, we typically use 90% errors. I'm sure there are some optical people or more optical people in the room who might disagree with me. But so if I say error 1, I have it set to give me 90% errors. So it's the confidence range of 2.706 is 90%. So you can, you don't have to use 90%, but that is the default in XSpec, and good reason for that, because X-ray astronomers are always right. So that tells us that the photon index should be 1.63 plus 0.36 minus 0.32 at 90%. So you see they're not symmetrical error bars. But the other thing I want to show you is we want the flux in terms of ergs per square centimetre per second. This is the observed flux, so I haven't removed the absorption or anything, but this is just to show you what happens if you forget an ARF. So we have a measurement here of 2.8 10 to the minus 10 ergs per square centimetre per second. I'm going to remove the ARF file. Does that delete the response as well? No, but if you delete the response, then yeah. Okay, so I've removed the ARF file, but not done anything else. So remember my flux of yes, I'm going to. Remember the flux is 2.8 10 to the minus 10. I'm now going to fit it again. I mean, it's actually gone nuts. Let's see if I can get it to go back. Well, I suppose I could have frozen it and refitted it, but anyway, it was about 2 10 to the minus 10. It's now telling me it's 2 10 to the minus 8. So a factor of 100 different, simply because we forgot the ARF or purposefully removed it. So as Andy said, it is really important to make sure your ARF file is in there, otherwise your fluxes are going to be wildly wrong.
It's a plot effective area in that.
Yeah.
That's basically just the QE of the CCD detector. If you put the ARF,
that's quantum efficiency. People might not know that.
Put the ARF back in.
Yeah. Okay, so watch the screen. It's peaking at not quite 1. I'll do that. and it's a different shape, and it's now at 100.
It's not got the mirror area and all the translation.
Yeah, so there's all kinds of calibration things in there. Right, this is taking longer than I was anticipating, so I better move on. So that's it for XSpec for now, because I want to show you how to do pilot correction in XRT. I think that was only the only other thing I want to do. Yes. So I'm going back into XSelect because we just did the window timing stuff previously, but now I want to read in the photon counting event list. So commands exactly as before, but it's the PC underscore PCW3 PO underscore CLD .evt file. So again, I'm going to do the filter PHA cuts, and I am starting to abbreviate things even more, as you might notice. But just like before, if I extract a curve, if I plot the curve, this time we have 2 snapshots of decent data, and that's because it was window timing nice and bright at the start. It's now fading in PC mode, but we kept observing. So I happen to know that the first snapshot is piled up in this case. And so the whole point of this is to show you how to deal with pileup. So what I want is an image of the time interval you think it might be piled up. Assuming you're looking at anything that fades, you should never contemplate more than 1 snapshot at once to see if it's piled up, because if it's bright and then faint and you combine the 2, it will probably say, yeah, on average it's not piled up, whereas it may well have been at the start. If you use our XRT, the user objects online, it does it more carefully than this. So I do it on a per snapshot basis. It checks constantly to see if there's pileup. So if you have 100 seconds of pile up and then it stops being piled up, it will account for that and only correct the bit where it's piled up, and only use the annulus and therefore save counts. But as a human, it's so much easier just to do it this way, which is another reason why using the online product generator is actually generally better. But so what I want to do is filter. I'm going to use the cursor option. You've seen all of them now. But I just want an image from that first snapshot. So I do that, filter there, and X when my cursor's in there, and extract image, and save image, and I'm going to call it PC1. So to check if something is piled up, we use this other tool called XImage. We can either come out of XSelect to do it, or as I mentioned, you can precede a command with the $sign and we can run it without coming out of XSelect. So read in the image, so read and the name of the file. And as I mentioned fairly quickly this morning, but it is nice to know, CPD for change plotting device, XTK. The XTK option for plotting things, I think only exists in XImage. I don't know if there are any other tools that use it, but it's great. So if reminder, you don't type plot in XImage, which is the one irritating thing, you have to type display. But this is XTK, and this allows me to zoom in. I can zoom out again if I click with my left cursor, so you can't really see where my fingers are, but if I left click, it zooms in and centers where I'm clicking. So I'm just going to zoom out a bit. So as I mentioned, it's generally a good idea to type the back command to get it to average the background before you start doing other things, because sometimes it will fail if you don't. So if I simply type back, it works out what the average background is in the field. We don't need to do anything with that, but it just helps with the PSF fitting. So I'm going to zoom in a bit more. You can see that column straight through pretty much the center of our source in this case, which is why the exposure map will be very useful, because that will correct the lost counts. But to do the PSF fitting, what we do is PSF curve, so PSF cursor, and then carefully clicking not in the image but onto the window, because what you then want to do is click as close to where you think the center of the point spread function, PSF, is. So about there, and then 30, 40, well, 40 or 50 probably pixels out. So we know that the PSF will have faded pretty much back to, I was going to say background level. So I just clicked in the center and clicked where I wanted to go out to. So we have this plot that I showed this morning. The only thing we care about are the cyan points, the light blue ones. I find it easier to plot all the to turn off the plotting for the other ones so it doesn't distract me. When you've used these things often enough, you'll learn that cyan is number 5 in the color scheme for all of these things. So if I say color off 1, 2, 3, 4, and 6, it just leaves me the 5th thing that it thinks it's plotting, which are the ones in cyan. So if I just say color, oh no, I can't do it at this bit. There we go. And that lists the color orders. So you see light blue or cyan is number 5. I know all of them up to number 8, and I know number 14 and 15, and then the ones in between I have to look up. So what we're going to do is fit the PSF model that we know is correct out to the wings and see where it diverges. So the psf.cod file is on our website. I listed it in the slides as to where to get it from. I'm pretty certain I have it. Yeah. Right. So I'm not going to the website to download it. I've already got it. So to fit anything in iPlot, interactive plot, command is model and then the name. There are other models you can do, but in this case, it's this COD file. And the only variable in this is the normalization. The rest of it is the actual shape of the PSF, and that is written into this hideous reverse Polish notation equation. So you may remember on the slide this morning, I showed what the equation for the PSF was. It's a Gaussian plus king with parameters and subscripts and superscripts and all kinds of things. In reverse Polish, that's what it looks like. We're not doing reverse Polish today. So what we want to do is fit this to where we know it won't be piled up, and then extrapolate backwards to see where it separates off. So in this case, so you don't say ignore the thing, you just rescale to go out to the radius that you want to fit outside. So if I say rescale X, and I'm going to say 15 because 12, because I know roughly where it's piled up from. It can be trial and error, but you're always going to want to exclude at least 10 arc seconds, maybe more, to do the fitting, just to estimate what it is, not then actually exclude. But there we have, so there at the bottom, that's where the shape of the PSF, but we haven't fitted it yet, so the normalization is wrong. If I type fit, and then plot, you can see that it's pretty well fitted there. So what I'm also going to do is fit plot 100, which smooths the fitting bit, so it interpolates between the points. So 100 points, it just makes it look smoother and easier on the eye. So now if I say rescale everything, just rescale, it's showing the bit that we ignored for the fitting. So we were fitting from about there, and it's separated there. If we say log off, that plots it in terms of in linear space, and we probably want to zoom in a little bit there. So I shall say rescale X from 0 to 20. And there we see that the PSF model is good to maybe about 15 arc seconds in this case, and then it starts to the XRT data are under where they should be if they weren't pile up. So in this case, we'd probably want to exclude about 15 arc seconds, which is what, 7 pixels. I can't divide by 2.36, but so I'm not going to do Python, but yeah, that you basically look for where it separates, where the line goes above the data, and that's the annular exclusion region that you should use. And then you can do everything in XSelect the same way. You define an annulus. Hold on, let's come out of this. So I don't have, I'm back in XSelect. So I just came out of XImage, but we ran it within XSelect, so it's there. Whoops. So there's the XRT image. So if I set an annulus, it's good good practice to make sure it's properly centered by typing in the actual coordinates, but I'm going to be really lazy and do it by eye here because we haven't got that much time. So if you want to do it in arc seconds, you can. I'll take, whoops, wrong thing. But if you're like me and decide to do it in pixels, then I would say, no, 7, excluding the essential 7 or so for this, would be enough to exclude pileup. Note that if you're not used to setting regions in DS9, you either change the radius there, or if you change it here, let's say I decided I actually wanted to exclude 10 pixels instead. If I just said that and typed apply, it wouldn't work. It reset it to 7, as you see. If you type it down there, you have to say generate, and then it does the numbers in there, and then you can do it, which is, then it will do the 10 pixels, which is why it's just easier to type it in there entirely. I have no idea why it's designed like that. So then I could say, you know, region, save, and call this. I'd rather do them one at a time. Though. Yeah. Yes. So I would tend to call it and7.reg, so I know what the number is. And again, always save in terms of WCS. So at that point, I could do what we've done for window timing. I'd go in and say filter region, annulus, and extract the spectrum or the light curve and whatever, and an event list if we wanted the spectrum for just the single snapshot, so that we can do an R file to make it match up. Right, so that is XRT that I wanted to go through. We can very quickly go through a bit of UVOT. I'm taking slightly longer than I thought I was going to, so I don't know whether we need to stop at past for the coffee break, or and then come back for maybe a little tiny bit more, or I don't know. It won't take much longer, but I don't know whether the catering people would get upset if we were, 10 minutes more. Yeah. And I also don't want to keep you guys from coffee, but the UVOT analysis, there's not as much to go through, so it won't take anywhere near as long. I'll certainly start. Yeah.
It's more homogeneous.
Yeah. Okay, so I've gone into a different folder here. So I'm using a different GRB as an example for this, because the GRB I used for XRT, I'd gone through it all and then realized that it wasn't one with a useful UVOT detection. And I'd already planned I was going to use that as an example. So that's why we're not using one specific GRB for both XRT and UVOT this time. So sorry about that. But I have picked one that has detections in lots of filters so that we can see what we get for the various things. So what I have got here are all of the UVOT images for all of the observations for this GRB 250807B. And so let's just, right, so first thing, I'm only going to do this for one of them, but I said previously you should always check that the aspect correction is direct, because if it's not, then the not aspect corrected and you won't be able to add things and it won't be much use. So again, we have all the different filters. We've got UU, BB, VV, all of those. So I'm just going to pick this first one to start with. Right, so UVOT image in the U filter, and being prepared, I already have an extraction region at the position of this source. So that is a 5 arcsecond radius region that we will use to do for the source. And oh no, I don't mean save, I mean open, to show you that what I'm going to use for background is a bigger region, but I'm just going to use a circle. In this case, you see there are no sources nearby. You don't need to worry about contaminating sources. You could use an annulus if you wanted, but you know, it doesn't really make any difference. So if we just want to work out a magnitude for one extension, we would use UVOT source. So UVOT source. One handy thing to include is centroid equals yes. So if my centering of the extraction region is not absolutely perfect, the centroid equals yes ought to shift it just a little bit. If it's a lot off, it won't work. I mean, it can't. If you drew your circle over there, it won't move it to the right place. Whereas our XLT product generator, the online product generator, can usually find your source within an area of a few minutes. Okay, so UVOT source, centroid equals yes. Oh, well, I will show it does prompt you for things. So in this case, I want to do the first extension of the U-band image of the very first observation of this GRB. So it asks for the region files, and I need a return, not a tab there. So source and background region files. Background threshold, I want it to be 3 sigma. I want it to be at least 3 sigma detected. And then the fits table of the values, this is what it will save it to. So I'm going to call it segment 000 u.fits, because I've got lots of these things. And as I said, it writes stuff to the screen. So if we just whiz back up there, there we go. It tells you the position, the RA and DEC of what we've imported. It tells you what the exposure time is. And then it tells you the Vega magnitude, but also the AB magnitude. So whichever magnitude system you prefer, it will give it to you. We have both statistical and systematic errors for UVOT. Strictly speaking, they should be combined in quadrature if you want to take them both into account. Some people will just give the statistical error rather than including the systematic, but it's a good idea to combine them both, really. And it will also tell you the fluxes and the corrected rate, and I'm getting random ODS Slack messages. So those are the things that are written to the screen. If I just open up that file, and this here I'm just going to scroll through. Again, you may not be able to read all of it necessarily, but whoops, come on, you can drag. No, apparently I can't. I'm just going to click down then, because I could do all of these columns exist. So there's so much data, so many things, measurements. There's fluxes in multiple units. It tells you what the minimum, how faint you'd be able to see it, how bright you'd be able to see it, and things like that. But generally, it's probably just the magnitudes and the fluxes that will be of use. The alternative to UVOT source is UVOT maghist, which will do multiple extensions. If it's one image with more than one snapshot, it will do those, or you can give it multiple images and it will go through all of them. So let's just do the one that we've just done. Whoops. So the one that we just did, I just did UVOT source for the first snapshot, but there were 2 snapshots there. So if I say u_maghist, again, you can't overwrite files, so I'm giving them different names. It will keep with a consistent naming. u.gif. So it will produce me a plot, which may or may not be useful. It's often easier just to take the values, the measurements it gives you, and make your own plot, because the default plot can be a bit messy. So I've given it the same regions. So as it did for UVOT source, it's written things to the screen, but this time there are 2 snapshots, so it's done it for both of them. And if I just look at the image, or show you the image, we've only got 1 snapshot. Why have I only got 1 snapshot? This one did have 2, didn't it? Am I going mad? I might be going mad. It did have 2. 15.
Look at the command where you created them.
No. Sure, this worked when I did it previously. Well, I mean, I can also show you how to do it for more than 1 thing. Well, let's do it with more than 1 image, just to show it'll do it for more than 1, and I'll figure out why it was misbehaving previously. So if you want to give it a whole long list of, so UVOT_maghist it'll want you to do it with 1 filter. So if I say what I want is all the U-band filters. Yeah, oh no, U. So in this case, we have 4 different U-band filters. So I'm just going to make a file called u.text. So I can show you how to read these in. So literally just a list of images, 1 on a line. So now if I say UVOT_maghist, I can tell it to do these instead. And I'm just going to call it uall.bits. And I will again call it uall.gif. You run out of ideas for names after a while. So you can see it went through them there. Display uall.gif. And there we go. Here we have a fading light curve. I mean, here, these are actually upper limits, as in it's fainter than that. They weren't detected in those. Always seems weird to say an upper limit when actually magnitudes go in the wrong direction, but you know what I mean, I'm sure. So UVOT_maghist will do that for different snapshots. But if you want to combine them, so for that one, some of the images were too faint, you might want to add them up. So that's the other thing that we'll do. So UVOT_IMSUM, as I mentioned earlier, we can tell it to add up either all the, I mean, I could make an average of all of those if we wanted. That seems a bit daft because it's fading. So, you know, why would you want an average for the bright one and the faint one? But let's just average, just to show you how to do it. I really can't type today. There we go. So I'm taking the first observation, and there were 2 snapshots in there, I hope. And I'm going to tell it to add those together. So seg sum.img. And therefore, we have a summed image, I hope. So I'm just going to check the exposure times. Seg u_sum. No, it's only doing one of those exposures. And oh, I know what it'll be. It's image plus event mode. So it does weird things. See? Let's do a different one. Oh dear. This is because I tested it on a different thing. I thought I'll do a different one today. Let's choose a later one. No, that's only got one in, for heaven's sake. They all only got one in, which was the one that I saw that had two. Yay, that one. Okay, so you've got in some. If I were to run it on this, I mean, honestly, the command is exactly the same, but just to show this one, I'll call it seg2 sum. And now if I to UU sky expert, that's not how you spell expo. Seg2. There we go. So the two snapshots there, one was about 295 seconds, the second was 155, and now we've combined them and we've got one image of 450 seconds. So the other thing, there are two more things that I wanted to show for this. One is UVOT product, just to show you how it works. So UVOT product will go through everything and build you all the different light curves in one go, which will is great if there aren't any on the bad parts of the CCD, which is the last thing that I want to show you. So these are the two things to do. So in order to no, not that dot. I think. Do I have? Yes, we'll ignore the fact that I call things poo.text. Sorry. Let's just do this a different way. So what I'm going to do is so I'm going to make a list of all the files. So I'm telling it I want one file on a line, all of the files that we have, which are the sky images. So just to show you what is there, we have segment 0 at the top, U, V, white, B, all of those for segment 0 there. Then we have segment 1, segment 2. So that's all the data that we have for this specific GRB. So if I run UVOT product, called it files last time as well. So I'm giving it the list of files. It's the source regions are the ones that I had before, and we're going to call it poo.text because that's what I left and I haven't changed it. So at least it wasn't ruder. As I mentioned earlier, the BAT XRT UVOT ground positions, just ignore them. Yeah, we're sticking with poo and poo.fits. So this will produce a text file with a whole load of information and a plot, well, two plots actually. It will do one for the V, U, and B filters, possibly with white, I can't remember. And so there's the optical ones and the UV ones. They're done in two different plots, and white is shown on one of them, and I can't remember which. You'll see in a minute when it gets there. But it will take a little while because there's quite a lot of data to go through. So while it's doing it, a reminder of the other thing that the reason that UVOT product isn't absolutely perfect is that it doesn't take into account the sources that fall on the bad spots of the UVOT. So if you run UVOT product or UVOT maghist and a source is on a bad spot, it will come up as 99. And I've got an example of that to show when this has finished running. But UVOT product knows that it's there and then it just ignores it. So this is, are you going to be quick or am I going to, oh, no, you're going to, where are we? So number 2, 3, 1, 2, there we go. It's speeded up a bit. So I can wait for this to go rather than doing something else while it's doing it. But what UVOT product does is try to bin the things together to get detections if it's not being detected. So it will produce two plots, as I said, for the different filters. So I've got Gwenview installed, which is, will allow me to open them both at the same time. Right, so there we go. So, so white goes with the optical filters. I suppose it makes more sense. We have a light curve, you can see, fading away in white. And so in this case, it was detected in all of these, and there's the UV one as well. So we did, although it tries to add things together to get detections, if they're too far apart, it doesn't. So you can fiddle around with it to try and tell it to merge more things, but honestly, it's black magic as far as I can tell, getting UVOT product to combine things. But the really useful thing is it gives you a quick and dirty light curve to show that, yes, we have detections in these and it's fading, which is a fairly important thing to know for GRBs. Yes, in all filters, you just give it all of them. So the other thing, as I said, was to show you what happens if a source falls on a bad part of the CCD. Now, you can't see this by eye. So if I just demonstrate, open up this image, there's a coincidence loss one, by the way. So that's where the source is so bright, we get this sort of square pattern around it because it can't correct for the mod 8 noise. But so this is the source that we're going to look at. I know it's one that falls on the bad region because I went through a whole load until I found one that worked. But looking at that, you would have no idea that it was in a bad part of the CCD, and that's because it's just lower throughput. It's not like there's a bad column that you can see as there is for the XRT where things are masked out. This is just slightly lower throughput. So if I run UVOT source on this thing, and my region file is 5 and 25 again, still want the background of 3, and I'm going to call it test because I can't overwrite the one that's there. And there you see source magnitude is given as 99, and that tells you that it's in a bad part of the sky. As I said, for some random reason, the fluxes are not given as 99 or whatever, but the source is not, the magnitude is 99 and the source count rate is given as negative. But basically check your magnitudes for anything that you're interested, anything that you look at. If you get a 99, it means you should ignore the data. There isn't a way to correct the data, unfortunately. If it's on an area of a bad area of low throughput, there isn't a correction factor to bump it up to the right value. I know the UVOT team were looking into it, and I'm not sure if they thought it's not possible or if it's just more work than they've had time to do yet. But long story short, if your magnitude is flagged as 99, you can't use it.
Do you know how many bad areas there are?
So there's a paper which actually shows them that was either led by Rick Edelson or by Jonathan Gelbord, but there's also a UVOT calibration document that I am 99% certain I put in the slides. I will check that, and that actually shows you where the bad spots are. So there aren't a huge number. I mean, we can't avoid them. And it depends how many UVOT observations you look at. But the one that I showed you that we use for UVOT product for the GRBs, all of those were actually good because I went through and checked them all, and that was a quite a big selection. So there are quite a few areas, and they're different in different filters. So just because something is flagged as bad in the V filter doesn't mean it's bad in the UV filters. So the V and the optical and the UV filters have slightly different areas that are bad. Okay, so that is actually all I wanted to do going through step by step. You can now have a coffee break, and then after the coffee break, you're welcome to have a go at either ask direct questions or have a go at some of this data analysis on your own and ask us if you get stuck, or if there's something specific that you want to know that we haven't been through, do ask. XRT, we ought to be able to answer just about everything between us. UVOT, I can answer quite a bit, but not absolutely everything. So no GRISM and no readout street, please. But yeah, so coffee break time, and then back here to do whatever you want. Okay, guys, I'm gonna stop presenting. I did.
Can I have a quick question, please? Thanks for. Hello.
I can hear you.
Oh yeah, great. What about Kim?
Sorry. What
Yeah,
you were
yeah. Sorry, I would have like a very quick question. It was not clear to me that you mentioned the corrected light curve when you were doing the XRT light curve. And what kind of corrections are included? Because like, as I noticed that when you were doing the background light curve, it was not corrected. And then you were subtracted one from the other. So what kind of corrections are included?
So the corrections are for the, if the source falls over the bad columns, that's the main correction that is done. So bad columns or the bad pixels. So it's, or the, well, I mean, that, and if you're using an annulus, so if you exclude any of the PSF, so the XRT-LC core basically does PSF corrections. So if you're using an annulus, it corrects for the loss counts from that. If it falls over the bad columns, it corrects for the loss counts from the bad columns. Strictly speaking, the background probably could be corrected, but I mean, you can also choose more carefully where to pick your background. So you could actually look and make sure that you don't put your background anywhere near the bad columns. Of course, you can't choose where to put your source region because the source is already there. So yeah, the XRT-LC core, that's what it does. It corrects for loss counts from the using an annulus and or the bad pixels and the bad columns.
It basically uses the model of the PSF to make the correction.
Yes, I don't know if you heard Andy was talking off to one side there, but yeah, it looks at what the PSF should be and corrects it at that. It's what the R file does for the spectrum, but it was written for the light curves.